Hello, welcome to the session 6 of the HackOn Data workshops. If you are listening now, please either send a message on the Slack channel or on the Google Hangouts. Thank you. All right, I think we can start. Okay, so if we are good to go, then let's get on with today's session. So today on Hangouts, I don't know what the issue is. I think I have to invite you personally to, let me see. If I invite you. Okay. So it's how to join. So you can click on the, let's see, if you, Okay. All right. So let's start now, and we can, as more people join, we can then ask. We can try to solve other questions. So today's lab was about linear regression, and the idea here is that you have a set of data, and you have a predictor variable. So in this case, the lab was using the million song data set, and the idea would be to predict what is the year of the song based on the given features. So typically when you have some data like this, the number one advice is explore your data before you start doing any regression. I mean, certainly building a model is very straightforward, and then most likely if you were to do so, you would probably get not very good results. So it's better if you can do some data exploration. I think this lab guide you through that very well. So the first thing to do is read the data. So very simple, everything was done there for you. And then just making sure that the data is there. You can use the DB utils to make sure that the text files are where they should be. And then initially you can see how many points you have, so you can simply use the count on the RDD that is produced. At this point you guys have read a lot of RDDs, so that is not a problem certainly. Then the next is to use label points. So MLlib uses this instance of label, or this object label point, and what it does is it tells the whatever algorithm you do in the regression or in classification, etc. What are the features that you have, and what is the target value. So in this case, what we're going to build is, given that the data that we have is in a text file, the first thing we do is we extract the first element of each line and then everything else. So this is just a Python list. So we take from the element 1 all the way to the end, and then we pass that to the second argument of label point. So label point takes a, so we can always go to the label point. Let's go to the API. So it takes the first element is a double, and the other one is a vector. This is the Scala API, so we can just go to Python. But similarly here, and here we see the label point takes label and features. So the idea is that we're going to give back into that format. So very much you guys are familiar with all this procedure so far, this sort of transformation. So I don't think anything advanced there. Here's where it starts getting interesting. You want to do a data exploration, and then here, yes, sure, we don't remove features, but maybe there are features that are more important, or features that have some noise, or they're garbage that maybe we want to remove. So then that's why this part, the visualization part, is important. Here you do just one plot, but typically you can start doing histogram over each one of the variables. So I think at some point somebody was asking about the scatter matrix, and that what it does is plots the correlation, or a scatter plot between each one of the variables in the set, and then in the diagonal it plots scatter matrix. Um, but something like this. So in the diagonal, you have the histogram of each one of the variables, and then on the off diagonal, you have the scatter plot of each variable against each other. So this is useful, and in principle, or by definition, it should be symmetric. So what is below the diagonal is the same thing that is above. And this would give you an idea whether your data is requires some cleaning or some other sort of pre-processing. Then the next thing you do is it has to find the range. So that is already we have the raw data, and we know what the label is, which is sorry. Here we extract the label, which is accessed by doing .label, given that x at this point is a label point, since we already parsed it, and we take the first element. You could do it either by doing also taking only labels, which is only the labels, and then taking the min from that, or you can use take order. So here I show both examples. So then we know that the range in this case is from 1922 to 2011. And just for demonstration, the same result you would get if you do that min. All right, so we'll go up to here. So then, so the one thing you could do is to shift the label. So in this case, is taking the minimum. Oh, parse data here. Okay. One thing you can do is starting from just shifting the labels instead of starting from 1920, you move them to start from 2020. So this is an example of the sort of pre-processing that you can do, and the only goal is so you have maybe easier to model features. So yeah, and sometimes shifting doesn't do much, but I guess here is also serve as an example of by looking at the data, you might and getting some insights in the initial exploratory phase, then you might get some idea of what sort of maybe transformation you can do. So for instance, if you see that, say, all your data is bunched up in one particular region, you might want to stretch it by applying a nonlinear transformation. So you might apply a log function to a particular variable. So that is the sort of transformation that then is going to help you create a better model. Sometimes linear models, people think them as very weak, but in fact, if you, in a way, apply all those transformations non-linear, or make sure you clean your data very well, linear or very simple models actually work better because they're easier to explain. The next thing we do here is to split the data set. So we take 80% of the data for training, 10% for validation, and 10% for testing. And we do that already. We have parsed the data. I call the function random split with the list of weights. And I think we have done something similar before, so I'm going to go over that quite. There's not much to gain there. So one prediction that you can do is to give everybody this, or give every input the same result. So for that, we can calculate the average. So similar to what we have done in previous sessions, you extract first the label, which is the year, and then you would find the sum total of all the years, and then you do that by using a reduce function. And then since you have already the number of events that are in the train data set, then you calculate the average by dividing the sum over the number of years. So how do you define the goodness of a fit? There are many different metrics. One of them is the root mean square. We went over that last week as well, but what it does is it takes the value of the prediction minus the actual value, in the case that you know what the actual value is. Of course, this is for testing and training. Takes the square of that, takes the square root of that sum, and so I think maybe I'll just show it. It's easier to see it. So it's the sum of the square difference divided by the number of events. So so then we will define a function that takes the label line of prediction and then calculates what? Oh, I see what happened here. So this was in my debugging, so I'm gonna delete it now. So we calculate the square error first. First we calculate the square, so the difference of the two label line prediction. And then we take the square root of the sum, which is this part highlighted, divided by the total count. Next, what we can do then, if we have the train data, we can come up with the prediction. In this case, we decided that the prediction for everybody is the same. We're going to give the average train year. And so we do the exact same prediction for the three data sets. For the train data, okay, no, sorry. Here's only for the train data, and then we calculate the root mean square. So then in principle, the prediction quality is not very good. So this is nevertheless, this is a baseline that we can use to then later compare and find ways to improve the model. So in this case, if we want to make a plot of how this prediction looks, oh no, this is the one. If we want to, what we're doing is we are predicting the exact same value for everybody. So not a very good prediction. Ideally, what you want to have is a straight line where the actual and predicted are the same number. So one way to find the minimum of the cost function, given that we're minimizing for the square RMSE, is to do a gradient descent. So a gradient descent, so what we're doing is we're starting an initial point of this particular function, this blue function, and little by little we're approaching the minimum value. So how do we do that? How do we write that? So the update that you would have, so you have an initial value for the weights, and that initial value on each iteration is updated by taking the derivative of the so in general, what you do is you define a cost function, take the derivative, and that derivative will give you the direction of the change. which will be in the direction of the minimum. So in this case, then this is the value that you would. How would you update the weights on each in each one of the steps? So then for that, then we we already have the function defined, so we just have to write it into code. And for that, we have two vectors. We have the weight vector and the features vector. So the weight vector is this W, and the features vector is X, and Y is the label. So if you look at this, it's exactly the same expression as what is inside the summon here. And then whenever we want to predict a value, what we do is we multiply the weights times the features, and that would be our final observation. And then, well, you have the original label, which when you want to check whether you are being able to generalize, you might not have the label, or when you have unseen data, that is something that you might not be able to find, but something that you predict with your weight time the features. So this is all set up for that. If there's any questions up to this point, I'm going fast today because I want to showcase some of the labs, some of the results that people had in the lab, in the exercise. And a lot of the topics today are in a way similar to what we've seen, particularly the manipulation of RDDs. I will share the solution at the end, so you can go and look at it in more detail. If you have any more questions, you can always ask again. So feel free, please ask now if you have any questions up to this point. And of course, I'm assuming that everybody already did this lab, so it's more sort of a quick overview. The next thing we do is then implement the gradient descent. So what we do there is we have the initial number of features. We initialize the weights to 0, and we have a learning parameter alpha. And we start with an error. So notice that the error is a number, and this number in principle will be reduced as we do more iterations. So again, the idea would be that little by little we are reducing the error until we get to the minimum. So so for that, if we have a given number of iterations, we start by getting the prediction, the current prediction, which is equal to the weight times the features, and we calculate the error associated with that prediction, and we calculate the gradient, which is the derivative with the function that we already calculated. Then we calculate the value of alpha, and finally we upgrade the weights, and we upgrade the weights multiplying alpha times the gradient. So what we're doing here is implementing the formula that we had seen before. All right, so then finally you want to train the model. So you decide on a number of iterations, how many times you do the update on the weights, and then you pass the train data, which is the one that we split 80%, and which is the input for this linear gradient descent. So we take train data and find the weights that minimize the error function. So if we run this, and then look at the RMSE, we see that compared to the baseline that we had, which was 21, we were able to bring it to 19. So a step in the right directions. So remember that the baseline is when we give everybody the exact same, or all the records the exact same prediction, which was the mean of the data set. So then this is a cool plot because it tells you that, yeah, you start reducing the training little by little, but then as you do more iterations, it seems like there is not much gain. You could, I guess, do this in a log scale. It is already in a log scale. And so then this is telling you that there is not much movement. So in principle, you could stop just around 10 iterations or so. You didn't have to go all the way to 50. Yes, here, well, actually here the same plotting log scale. All right, then we can actually use a library where we don't have to write any of the gradient descent, but already and there are, on top of that, there are some optimizations that in principle should make the calculation run faster. So the syntax is very simple, and then if you have any questions, I always suggest going back to the either the Python API or actual programming guide, which is very complete. So in this particular, let's just look reference here. If we look at the list of parameters that I require. So the parameters are data, the number of iterations, what minimization function you use, what regularization parameter you allowed. So in this particular, everything was, I think, set up. We already know what the training data is, so it is in the format that is expected, which is label point. And the number of iterations, which in this case was set to 500, and other parameters that were predefined in the previous cell. So if we compare then the error in this prediction, sorry, and then to predict, what you do is, so this training, which is the training that occurs here will return a model. This particular model then is then used to evaluate the features on the testing data. So for that, we will call the model with .predict, and then we will pass a number of points, and what we will get is the prediction value for that particular model. So then we can evaluate how did we do compared to the previous case. So that is right. So it seems like our or the built-in uh, stochastic gradient descent made it a little bit worse. So not much gain there. But that could be because we are not using the right parameters. So one way to build or to tune the parameters is to do basically a loop of training the same model over and over, but then changing one of the parameters, in this case the regularization parameter, which is the penalty parameter, and we talked about a bit before. And what that means is this parameter is gonna avoid some of the weights just to go very high, and then allow or prevent overfitting, more importantly. So then this is in a way very manual procedure, because we are generating the or creating the loop ourselves, and then in that case might not be as efficient. We're running also one at a time. We're working with a parallel computing framework, so in principle we could say run these three models all at the same time on different nodes or even in different processors. um, so in principle that could be speed up. So for those three parameters, we find that in fact we were able to bring the error from 21 to 17. So what this is telling you is that there is value in using or tuning the parameters of a model. This model in particular we're using or training just fitting only one model, but then it could be that you are training a more complex model and then you are certainly tuning more than one parameter. So the approach of doing a for loop might not be ideal. So Spark provides a functionality called parameter grid that would allow you to do that automatically. So then if we were to then visualize what this model is, we know that a lot of the stuff is very far from the diagonal. And then in principle is because, yes, the way we set up the model, if you think about it, we could have, instead of predicting the year, we could have predict maybe in intervals of 10. So what is, so from 0 to 20, 20 to 40, etc. So maybe we do a grouping of the data, and that might help improve the model. Or we actually need to use better features or use better models. So something like another, like a classifier or a nonlinear model might do better. But nevertheless, this was good for learning. But so yes, we know the quality of this model is not very good. Here's another similar idea as before, but this time tuning the alpha parameter. And the result is right. And then right, in general you could do many parameter search. So if you look at here, if you have number of iteration and regularization parameter, you could create in principle a grid. So there's a two-dimensional grid, and you would find which one of these values will minimize. So it would be this value here in this corner. So yes, sometimes tuning the model will take a lot of time, even if the model that you're training has or appears simple. By tuning the model, by tuning the parameters of this model, you can certainly gain. I'm gonna stop here for a minute, and just because I know Valerie has to go, and I want him to share his solution for this week, we can go back to talk a little bit more. Um, so this week, the lab was about, or the exercise was about linear regression. So very similar setup. You had a lot of features, and those features correspond to online articles. And the idea would be that you will build a regression model that would allow you to predict how many shares this particular article would be, given that you had features. So in real life, you spend a lot of time just doing the features. In this case, the features were already set up for you. So Valerie, if you could please share your screen so others can see what you have as you talk. So Valerie used R for his modeling. We have done a lot of things on Spark, so I thought it was a good idea to see.
Okay, thank you for this opportunity.
Yes.
Could you let me know if everyone can hear me?
Yeah, we hear you. We hear you. Go ahead.
Thank you. Thanks again. And my name is Valerie, and I've never had a title such as that data scientist, but I have been always involved in work related to data science in different areas, from signal processing to industrial automation and speech recognition and so on. So it gives me a lot of fun to be involved in exercises like this. So let's bring some sort of diversity and look at using of R language for exactly the same problem. Why R? Because it gives me a sort of flexibility, and as you will see, it's not so exhaustive to write a code in R. So since I'm restricted in time, just let me go over the solution and make some short stops on the most interesting moments. So we always start with sorry, is it okay with such font size?
Yes, it's good. It's good.
Okay, thank you. And we start with getting and cleaning data. So just 2 lines of code gives us a possibility to look at the data, what kind of variables we have here. So we can see just a very, very common summary for our data set and description of variables. Some of them are recognized by R as factor, some of them are recognized as numeric, and so on. Then a quick test on the availability of possible not a number values. So then, as we can see, there is no such values or missing values. We can go forward and then look at the columns, our independent variables. Here, we usually try to restrict the number of variables and make the model simpler if it is possible. So here we can see that some of the variables can be omitted, such as URL, time delta, since they are non-predictive, then 5 LTA variables, and maybe is weekend. That was my first thought that we don't need is weekend because it seems to be duplicating. We already have days of week. And some of the variables which have negative values, I don't like them. Generally, domain knowledge and even a common sense helps in making decision on which variables we need to choose to build the model. Okay, so then we exclude those variables from the raw dataset and convert numeric variables to factors. I mean the variables which are factors by their nature. It is days of week and channel types. Okay, and now maybe it's time to have a closer look to the number of shares, because I believe there were a number of questions on what to do with it. And what I built here, it is a histogram of shares, and let me open the other plot. So here I'm trying to zoom in the area where the number of shares is between 0 and 5,000. So we can see that our distribution is heavily skewed with a very short left tail and very long right tail. So I cannot say what kind of the distribution is, maybe a sort of power law distribution. What I want to do is to take logarithm of shares, and on the next plot we can see that logarithm of shares has almost normal distribution. It is the theoretical distribution is shown by red curve. Generally speaking, it is not strictly required that it is not strictly required for outcome variable to be normally distributed, but we did this by some reason which I'll show you later. Okay, then we are creating all of the steps listed above we need to repeat for our scoring data set. So all of the steps in application to cleaning data and transformation of variables. Then we are trying to build firstly full model, which includes all of the independent variables. And what we can see, our system gives us summary statistics on this model. The most interesting parameter is adjusted R squared. So this parameter is a measure of the proportion of the outcome variable which can be explained by independent variables. So as we can see, this model explains only 12% of the variance. It's not so good. However, maybe there is a room for improvement of this model, since we can see that not all of the variables are statistically significant. Then we apply so-called backward selection procedure, which tries to find the model which contains only significant, statistically significant variables, and it allows us to find some kind of the model which has different characteristics, but very close to the characteristics of the model noted above. Almost 12% of the variance explained in smaller number of independent variables, but all of them are statistically significant. Then I tried to build just simple model which has only one independent variable, just for contrast. It is obviously the poorest model. And then just before we look at the variables of the of our best model, which is our best choice, I wanted to show some tools. It's only one of the possible tools can be used to test the models, and they just probe your data in different ways to diagnose possible problems with model. However, what we can see on these charts, the first one shows that there is no consistent pattern supporting the accuracy of the independence of the variables. So sometimes it's possible to see temporal patterns on this chart in cases when let's say the order of taking points or the order of taking observations is important, but here we don't see any patterns. This is just random values. Then maybe the most important chart is normal QQ. This plot indicates that the residuals are normally distributed. Ideally, the normal distributions is something which lies exactly on the diagonal shown by dot line here. And that's the reason why we took the logarithm of the number of shares. So we can completely spoil this picture if I comment just 2 lines of code where the logarithm of shares is taken. So this picture will be completely different. Maybe later I can show it. So just to, sorry for not having enough time, just to show the RMSE value for this model. If you can see, it is 0.88. So is it good model or not? It's difficult to say, because even with this model, I can see there is a room for improvement. For example, if we look at independent variables, we can see that variables such as day of week, all of them are present here. Monday, Tuesday, and so on. And maybe it will be much better to use the variable is weekend instead all of them. So I didn't try it yet, but I would like to try. More than this, if you build some cumulative statistics, such as aggregated number of shares versus this variable is weekend, you will see that the total number of shares is very different for weekdays and weekends. But in average, the average number of shares on weekdays and weekends are almost the same. It is about several hundreds. However, when you run the two-sided t-test for the average values, you will see that news released on weekdays and weekends belong to different population, and that makes sense. It gives us the right to use, for sure, to use the variable is weekend instead all of those variables which characterize the day of week. So let me try to comment 2 lines of code I noted. Okay, where is it? This one. This one. And I expect to see how bad the model now. Let's wait for a while. Okay. Okay, while we are waiting for this, just let me say again many thanks to Apache Spark community, and especially a lot of thanks to HackOn Data team for your feedback and for this opportunity to represent my work.
Yeah, thank you, Valerie. It's very detailed.
And I really want, okay, it's finished. Then, yes, we have model. And, okay, do you see this? The worst thing about this is the residuals are distributed. I don't know how. It is not normal distribution. So this is strict requirement for residuals to be normally distributed. And yes, there are outliers maybe here. And the final measure, and this is a root mean square error. So I'm wondering if someone else guessed to take logarithm or apply some other kind of transformation to the variables to get better results. Oh, thank you, Vlad. I see your comment. So thank you for your attention, and I think I need to rework my model and find a better solution, maybe with other variables, and maybe it would be a good idea to publish it a little bit later. Okay, thank you.
Yes, thank you, Valerie. I will share your notebook with everybody. And And then, yes, I'm sure. I think there are some questions now. If you don't mind answering. One of them is when you do the log of the shares, what happens to the entries that have shares equals 0?
Just take logarithm of shares plus 1.
Okay. Oh, I see. You define the transformation plus 1. That makes sense.
Okay, thank you. And if you have any questions, just PM me or ask questions on HackOn Data Workshops channel. I'll try to reply to all of them. Thank you. Have a good night.
Awesome. Thank you. All right. Okay, so hard to beat now. Pretty good in-depth analysis. I think that is great. And the beauty of Spark is that you can interface with Spark R or Python if you need to do any plotting, etc. So if you are familiar with those, you can always complement whatever you do with Spark to make it distributed and then be able to tackle larger problems. Well, now we have another showcase, and this time is this one is based on Scala. So I will similar. Let me just give control here. So Noah is been very active in the group as well, but he writes all these programs in Scala. So Noah, whenever you're ready to take it, please take share your solution and tell us the approach you use. But please, everybody, bear in mind that this is Scala. It's very easy to read, so you will be able to follow. But one thing, or the goal of the exposure in the lab was, if you notice, in the lab you did everything first yourself, then use the MLlib library, which is going to be deprecated at some point. So everything is moving to using the data frames interface, which is the Spark ML. So that was the encouragement of the exercise, that you guys would go and explore that interface. So I will at the end show my solution in Python, so you would see how we would do it in Python. But for now, let's go, Noah, if you don't mind sharing your screen, and we'll go from there. Thank you.
Okay. Can you guys hear me?
Yes, we hear you.
Perfect. Can you see my screen? It says I'm screen sharing.
Yes, we see your screen.
Perfect. Okay. So I did use Scala and MLlib. My results used some really cool features, I thought, of MLlib and Apache Spark, but my result was horrible. So I kind of went the other route. I actually, as the second I'm done, I want to go back and rescale my shares with a logarithmic scale. I didn't do that, and I think that may help correct a lot of the problems that I ran into. So that's a great solution, and I didn't do it, so my result won't be as good. But I'll skim through relatively quickly for the first part, just showing some of the exploration I did. I loaded in the data and I used the CSV. And I had an issue. I looked it up, actually. There's a bug in Spark CSV where these CSVs are being read strangely. So if you saw using R, it didn't seem to have that problem and knew what to do, and there were no weird spaces in the headers. But I had to do this little fix header function. It's small, but it was annoying. It would be nice if they would just fix that in the core. And then with the training and testing, the testing data set, loading it in, there was an issue with row number 8,429 had the header repeated. So everything came in as strings and I couldn't read them as numbers. So I converted to an RDD, kicked that one out, and then converted it back to a data frame, and then reapplied the schema. So a little bit of wrangling just to get the data in, but from that point forward, straight data frames. So that it was relatively straightforward to work with from there. Here's the schema. I took out the actual URL because we didn't need to know what it was. And earlier on, there was another variable mentioned that we didn't need if you were to look at the actual data source. It wasn't a real predictor, so I kicked time delta out as well. Did a quick comparison describing both data sets, the training validation and the testing data set, and they were comparable. There were some differences and there was some more variance. Standard deviation was higher on one, but for the most part, they kind of looked alike at a quick glance. So I started to get into just picking apart the data. So I didn't use a lot of the visualization features, which in retrospect, I should have started with instead of tagging them on to the end. But I actually started tinkering with a couple of models just to look at the R-squared, not using a training and a validation data set. I was actually running a model on the training set and then predicting and calculating an R-squared off of that same set. Just to kind of give it the best case scenario. So even if we overfit, how big of an R-squared can I get and how low of RMSE can I get? To do so, sorry, I'm skimming a lot. I set up some basic models. I set up a linear regression.
We have time. Don't worry about rushing.
Okay. I also set up a separate one where I wanted to run a PCA first to reduce the dimensions. So instead of trying to carefully look through each of the predictors, I figured, well, maybe if I throw everything into a PCA, let it reduce the dimensions for me, would that do the trick? It turns out it didn't, but it was a fun exercise to go through. And I dropped those instead of a features column, I called it a PCA features column. So this linear regression here, instead of picking up off the default features column, I told it here to pick up off of a new column. I set up two evaluators because I was interested in both. You can set up a new regression evaluator. Label column is label, prediction column is prediction. But you can set the metric. So RMSE for one, root mean squared error, or R squared, which we saw in the last demonstration in R, a very useful metric. I also set up some formulas. So this was kind of cool for me because I have a background in R. Before I started learning Scala, all of my data analysis was done in R. So I really like using R. And I saw this. There's R formula. And I know they have it in Scala. They may have it in Python as well. But what it lets you do is it lets you use an R model formula in Scala or in Apache Spark at least, which I thought was super cool. So this one right here, it takes shares, and then the little tilde is by, and the dot means everything. So if I'm just throwing everything in, shares by everything, very simple to do. But then I thought I would sift through a little bit more. I saw that somebody did take the time to do some topic modeling. There's LDA 0 through 4. So let's take a look at those on their own and see if that's somewhat predictive. I took the days of the week and I kicked out Sunday and weekend. And then I looked at some polarity. I took a bunch of those and just started exploring a little bit. To explore, I created a pipeline, and this is something I really like about MLlib. I do a lot of data transformations in my day job, so a little bit of modeling, but realistically, most of what I do is I manipulate data. I take data in one form, I reshape it, I summarize it, and I do all these things to it. The concept of pipelines is a way of tidying up that process and saying, first I do this, and I take the results and I do that with it. And you just run it through really an assembly line of data transformations or model training in this case. And it's pretty cool the way they do it in MLlib. My LDA formula up above is my first stage for this LDA model. And then I run my linear model that I defined earlier. So just to skim backwards, I'll show you both of those again. So I have my linear model, which is just a linear regression. And then I have my LDA formula, which is an R formula. So what's going to happen is if I run my data frame through that, it will call shares my label, and it will move that over nicely for me. And then it will create a feature vector for me that has these LDA columns. So that's what the first part of the pipeline does. And then taking that, it will run it through linear model, which is looking for a label and a features column in the data frame. So I do an LDA prediction. Sorry, first I fit it actually up here. So I fit it on the raw data, and then I transform it on the raw data again. So I know I'm overfitting when I do this, but I really wanted to see what happens when I try to overfit. And I did the same thing with days. Really same thing again, except I'm just swapping out the formula. Pipeline is identical, except the formula is different. And again, for polarity, pipeline is identical, but the formula is different. And then I run all my evaluators, and they were really bad. So very low R squared, so I'm really explaining no variance, and a very high root mean square error. And if you look at the root mean square error, it really doesn't matter what I was doing. It's kind of in the same ballpark. So I figured something else is needed. Great, we get to test out PCA. PCA is very similar. So they do have a constructor. You set your input column and you set your output column. And then you can set K. So I tried a number of them. I tried 3, I tried 5, I tried 10. It got a little bit better the more I added, so I settled around 10 just through interactive use. Ran it through again, except I used everything, which is my all formula. Scrolling backwards, I'll show you that one again. So it shares tilde dot, gives me a very long feature vector. And then PCA I was relying on to reduce those dimensions down from 50 or 60, whatever the number was, down to 10. And then I was running the regression again, but the regression is now looking for PCA features as my feature column. And a little bit better, now I'm 1% of variance I can explain, yay. But my root mean squared error isn't very different at all. So I'm improving one of the metrics, but I'm not really doing anything predictive here. My conclusion, PCA on its own, really did nothing. So I figured now I actually do have to look through my features and dig a little bit deeper. So I decided maybe I'll look at correlations. On the RDDs, so not on the data frames, but on the RDDs, I can do statistics.core. So what I did is I took my data set, converted it to an RDD, and then converted each row to a vector of doubles. So a little bit of mangling or transforming my data, just because that old RDD API, although they're going to deprecate it in MLlib, it still has more features than the latest and greatest data frames, data sets API has. So in the meantime, they're not going to deprecate it because it has all those nice features. And we have to do some data transformation. But soon, in the near future, all of those features will be migrated, so they say, to the data frame API and the dataset API, and we won't have to do this anymore. But what it gave me was a big correlation matrix. It was so big that I couldn't display it, and I didn't want to take the time to convert it back to a data frame. So I just snipped off the bottom row, which was giving me the correlations of my share. And you see here there's a 1 because share is exactly correlated with itself. So again, instead of prettying it up here, I just dropped it in Excel and quickly picked up the indexes for the biggest absolute correlation. So either the positively or negatively correlated. And I saw these 3. So data channel is world, keyword average, and LDA topic 2. So I created a new formula there, redid my pipeline. Again, always the same thing. So this little bit here I'm doing with the pipeline is always the same. So far, the only thing I've changed is that first stage. I'm still running a linear model here, but that first stage changed. And I didn't really do much better. It's not bad, is my note here, considering I threw out most of the data set when before I had everything in. With R squared, if you put in more features, your R squared tends to improve, but it often doesn't mean anything in reality. It's really when you do that training and validation when it starts to mean a little bit more. So that was my note so far, and I figured, okay, well now I need to really dig in and spend more time with it. So I started fumbling around, and instead of taking a log of the share, which looking at that last demonstration, I really want to do the second I'm done this call, I started looking at different ways of bucketing. So let's say, well, above or below 1400, or maybe if I broke it into bins of 5, maybe that would make it easier to predict the shares. So instead of the raw share value, here I'm doing binizer or binarizer is what they're calling it, but it's just another data transform. It takes my input column and it puts it into an output column, and I pick a threshold, 1400 in this case, and if it's above 1400 I get a 1, and if it's below 1400 I get a 0. So it's kind of cool. I could actually take this, and instead of a linear, I think I could do a logistic regression on that one. Here I took the same formula. I'm just restating it here so it's all in the same cell. And my pipeline is now a little bit bigger. I do my correlation formula, which gives me the correlated columns as a feature vector. And then I do my bin share transformation, which is just taking a 1 or a 0, is it above or below 1400? And then I'm running my linear model. And as you can see, ta-da, down below, I do have a higher R-square than I had before, which makes me feel a little bit better. But here my root mean square error is just below 50%. So it's small, but now I have a 1 or a 0. So if I were to flip a coin and say 50-50, I should get 50 here. So I'm just slightly below the performance of a coin flip, which is really not that good. So I kept going, and I tried different things. I tried buckets and bins and all that sort of thing, but I'll scroll ahead a little bit more and show you. I started Googling because I was actually getting annoyed that I couldn't find a good answer. And somebody wrote a paper about this data set, and they talked about how they used, I think it was an F statistic, to come up with, really all they were doing is they were coming up with highly correlated, so I'm just going to try to find what they said that was. Fisher criterion. So realistically, it's better than a correlation, but same general idea. But they did some sifting, and they found these 20 or so are better predictors than everything else. They said they were getting about 70% accuracy and recall. Accuracy and recall when they did their linear regression, 66 and 67%, which is much better than I was getting. So I thought, well, maybe I'll give that a try. And again, my R-square went up, which was, I think, the highest yet so far. And I had a number of buckets, so my root mean square error, it's not apples to apples anymore. But my R-square was the highest it's ever been. So this is good. I felt like I'm on the right track. Kicking out some noise and only looking at predictive variables is helpful. I tried it again with everything, and it got better again. So my excitement went away immediately. Picking these features didn't really make everything better, because when I throw everything in and use my quantized scale or shares, I improved again. So I'm getting these minute improvements when I do something slightly different. So again, I did everything in the reverse order. This is the first thing I should have done, not halfway down the page. And I see that, well, everybody said a very low number. I think that's in and around 1400 is the 50% mark. So everybody was either below or above 1400. And what I was doing is I was ballparking people somewhere in the middle, when realistically the distribution of those bins was intentionally evenly distributed. So at this point, I decided to stop exploring and start toggling model parameters. Again, looking at that last demonstration, what I should have done is spent more time massaging and improving my features, or my dependent variable, the shares, applying that logarithmic scale. But running out of time, it was due today, so I moved forward. I took a training set and a test set, and you see some commented out code here where I did initially do that 80-20 split, but I saw later on Spark MLlib has a training validation split. So it'll actually do both all in one for me and then pick the best model instead of having me sift through. So I thought that would be more useful than me doing training then validation. So all I needed was the two data sets as they came in. And what got really cool is you saw above where I was cutting and pasting and I was reinitializing my R formula. In one of the links Armando sent, it allows you to do that grid search, but I can also do the grid search with my feature selection. So I can do the shares tilde dot and include everything. I can do the LDAs, I can do the weeks, I can do those 20 or so highly predictive measures. I can actually get it to cycle through those. I don't have to cycle myself. I just provided an array and it will do the search on its own. Up to this point, I've always been using the default, which is 100 iterations. So I figured let's try bumping that up and see what happens. For the discretizer, try 2 bins, 5 bins, and 10 bins. And with PCA, let's try 3, 5, and 10. And then started to play with some of the other the regularization parameters. So this here is just initializing everything I'd like to toggle through later. I really like that I have the ability to put all my hyperparameters in one spot, in one cell for organization, and then later on I can apply them. Again, I restated my models, same thing as before. I have a linear regression and I have another PCA regression, I'm calling it. It's not a proper one, but it's close. The only difference is my column, where I look for the features. And here, when I do my R formula, I'm calling it column formula now. The one major difference from what I did before, two major differences, is I'm setting the column label as label 0 because I'm going to do two things, and I want to save the original label 0, and then when I actually run it, my discretizer, I want it to pick up label 0 and then output to my final labels. But the other difference is that I didn't give it a formula. Everywhere else where I did an R formula, I gave it something. Here I'm leaving it blank. And in my pipeline, still setting it up the same. So I want to do the column formula, do the discretizer, and then do the linear model. But this is what I really liked. And this is kind of opening my eyes to some really cool things about MLlib, is I can do a param grid builder. So I can add to the grid my column formula, that field that I left blank, have it cycle through those formula strings that I had initialized up above. Same thing for the regularization parameters on my linear model, lm.regparam. Tell it to go and look at that array, cycle through those. Same with the number of iterations and same with the number of bins for the discretizer. And what it does here is it does that combinatorial exercise. I don't have to do it. It does it for me. It saves me a ton of work. Evaluators, same thing. I'm just restating them down here. And I did a cross validator, which I later on ignored, but this train validation split. I set the estimator as the pipeline, set the evaluator, and this is important. So before I was just printing the evaluation, but here for it to do the training validation, it needs to know when it has a better model. So I'm giving it my R squared evaluator to say if my R squared is higher, it's better. You just tell me which of these combinations made it the highest. And then it does the 80-20 if I give it an 80 here. And here you can see the parameter map where it created all combinations for me. So drum roll, looking at the result, it got worse. This is actually the worst yet. That negative R squared means I've done something horribly wrong. My predictive model is not predicting anything. You never want to see a negative. So as a little dumbfounded, I ran through every combination. I had everything tidy as before, but I was playing with bins. So instead of the 1 or 0, I was playing with bins. And I didn't do my PCA that I did earlier. So I figured, well, let's try it again. This time, what am I doing here? I have the binizer, and I'm inlining the bins, the binarizer. So now I'm doing 1 or 0. So it's below 500, it's 0. Above 500, it's 1. Same thing with 1,000, 1,500, and 2,000. Running that and seeing what I get. And again, not much better. I still have a negative r squared, so that was disappointing. And just to demonstrate, I ran a regression evaluator, and I'll show you up above actually. Or maybe I won't show you that. Oh, right here. So when I did my prediction set, I selected the features, the label, and the prediction, and then I made a null prediction column saying 50. Because I have a 1 or a 0, if I just set the predictions at 50 and check out my root mean square error, it should be 0.5. So that was just to demonstrate 0.5 versus 0.83. Flipping a coin would be the route to go because my model in this case is useless. Used really cool toys, but produced a very useless model. So last proper attempt, I'm using PCA. Again, combining all of those hyperparameters, sifting through everything. I shortened the number of formula strings because PCA, I'm reducing dimensions. So if I already have a low number of dimensions, I don't need to reduce them further. So I took the ones that had a lot of dimensions, but everything else I kept the same. And in the PCA, I'm going to cycle through a number of bin sizes, a number of K. And I think finally I got a good result. This is actually pretty good. The R square is not too shabby, but the root mean square error is lower than 0.5, meaning it's better than a coin flip. But when I look at my data, so my labeled versus prediction, really all it's doing is it's predicting more than 500. So again, it's worse than a coin flip. It's saying, do you think a Mashable article will be popular? Well, if I define popular as 500 shares, then yes, every Mashable article is going to be popular. And if you say that pretty much every time, you'll pretty much always be right. So that was a little disappointing. I thought I finally cracked it, and I did not. So to be thorough, on this other screen here, just while we were talking, I ran one more. So I don't know if this got submitted for the assignment, but at least for my sanity, I did 1,400 above or below. And at least you can see here, the blue is the label, and it's just a line going up and down. It's not a proper plot. But you see that the line goes between 1 and 0. And at least my prediction is trying to edge further away from 0.5 toward 1 or 0. So at least it's trying to make a prediction. And I'm slightly better than a coin flip. So nothing earth-shattering, but this was the best I did. But for me, at least, the moral of the story was to use pipelines. I thought it was really cool how I can create a pipeline that will iterate through everything I'm thinking and just throw it all in and try it all. I can run it, and I can go do some of my other work, come back an hour later, it's done running, grab a coffee or whatever and come back. It sifted through everything, and it has picked the best one for me. But also knowing that I'm not done. This model really didn't work, so I have to go back and change something. I don't have to rejig my entire system. All I have to do is edit that one part of the pipeline that I think I can make an improvement. So one data transformation, if I were to add that to the start of my pipeline, the rest of the pipeline would stay the same, no changes. So I think it's really a very productive way to start building models, data transformations, learning something, and then going back and editing where log transform is probably what I needed here. if I were to do that instead of column formula, sorry, instead of the bin shares, um, I should have a more productive result. But knowing that it's just that easy, there's one part of the pipeline that needs to be changed is the coolest thing I've seen this month. Yeah. So that's the entire demo.
Yeah, thank you. That was really good. You spent a lot of time on it, and yes, definitely, a linear model is not gonna work for this particular example. So the way to improve it is, as you suggested, spending a lot of time understanding the features or combining the features, maybe multiplying the features. Which in the lab there is an exercise where you start multiplying one feature by the other, and then you see whether there's an improvement.
Yeah. On that note, actually,
Yeah.
that R formula syntax
Yeah.
allows you to add interaction effects.
Oh, awesome. Yeah.
Yeah. So it's incredible for just doing the legwork for you.
Yes. And exactly. I think with the demonstration that there are a lot of already things built for you. You don't have to spend time building pipelines. That is certainly beautiful, and where you're gonna be able to do a lot of experiments, which ultimately is what is gonna push you push ahead. So no, that's great. I don't think I have much to say after that explanation. Just I did something similar using Python, so I can share that I think offline, so you guys see how do you do some of that. So for instance, let's say this one here, where you select what are the features. So I have a number of features that I selected, and then this vector assembler does that transformation for you. So puts them into a column features, and then here I define my grid. So very similar, exactly what Noah showed us, but just with the Python syntax. And then you can use the cross validator to then go and find what are the best parameters. So this one in particular is already running. So one thing to notice that yes, you have the advantage that you can run many parameters. So remember that every time you add a parameter, you multiply the search space by 2, right? So you're increasing, right? If you have only 2 parameters, you have 4 combinations. If you add another parameter, you have an extra combination. Oh, sorry. Oh, my screen is not sharing. Oh, sorry. Oh, I see what happened. I selected the wrong screen. Yes. Okay. Sorry. So one thing to be careful is that yes, you have the facility to train with many parameters. Problem is that you can then start all of a sudden deciding, oh, you know what, I'm going to use 10 regularization parameters. So maybe doing an initial search where you have an idea of where, what value based on your experience. So very similar to what Noah showed us, that he had already some intuition of what those parameters were. And then from there, you can start doing those changes. So that I guess is one thing to be careful. I think you did a lot. You did PCA. We're gonna have a session on PCA for those who don't know what that is. The problem with PCA is that it's a linear transformation. So it could be that PCA can make things worse. So let's maybe we leave that for another session, given that we already passed another half an hour. But yeah, PCA, you have to be careful also sometimes with that. But yeah, no, thank you very much, everyone, for your attention, and particularly Valerie and Noah for the demonstration. And we'll share the links with all the notebooks. And we'll see you next week. So let's see. I don't think we have more questions, or maybe there is. Let's see. All right, so I'm gonna stop the broadcast now, but we can continue chatting on the Slack channel. All right, everyone, have a good weekend. Bye.